Our next speaker is Redi Haderi from Bilkent University, and he's going to be talking about enriched liftings and extension problems, whenever you want.
Okay, so thanks a lot for organizing this and for having me. It's been a nice, very nice couple of days. And we always say, like, the person who benefits most from giving a talk is the person who gives the talk, which has been true in my case. So my understanding of what I was going to talk has kind of evolved as I was preparing it. So topic I want to talk about is enriched lifting and extensions, which, I mean, it might be a poor choice of title, but let's go with it. Right. So let me just jump right through. Oops. Okay. So lifting and extending is something we are familiar with. So I don't know, from basically every field of math, I think. You lift or extend maps along another map. So in any category C, we can kind of consider lifting, extending. And so this is how we diagrammatically would express a lifting and extension problem. So I have, like, can you see my cursor?
Yes.
Okay, it's pretty important. Okay, so I have, for example, map F, map G, and we ask, for example, whether we can lift F cross G, or whether in the dual diagram here, we can extend G along F. So quick personal opinion here. I think the fact, I mean, one of the reasons category theory is so successful and popular is the ability to draw pictures or diagrams, in this case like this, to express some mathematical idea, because it's really powerful. So, I mean, I'll be sort of standing on this idea, and you'll kind of see why. Okay, so enriched lifts and extensions, what are these? So when we consider like a collection of lifts or the collection of extensions, sometimes there is extra structure. So my examples are from simplicial sets and spaces, but if you don't know what these are, it's fine. But these are just kind of examples. They will become pretty irrelevant, but just for illustration. So if we consider a map F, lifts of the identity are sections, but lots of time we want to talk about the space of sections, for example. So this is the boundary of the interval, which picks 2 points in X, A and B, and lifts along. So this should be an inclusion here to the interval. So the lifts of these are like paths joining A and B, but I mean, there is more structure. So the collection of these extensions form a space. So these are just examples. So first observation is that extra structure comes from an enrichment in the category the problem is present in. So what I will do, I will fix a monoidal category. So this is monoidal product I. This I here is the unit for the monoidal structure. And thanks to the people who kind of talked about this before me. So I'll assume you perfectly understood everything that's been talked so far. And C is an enriched category in V. So this is for the rest of the talk. So what my goal is to describe a way in which we can draw diagrams like this, in which the dotted arrow expresses the V objects. So L and E are objects in V, and they represent the V objects of lifts and extensions. So I will do this with double category theory, which has appeared in this symposium a couple of times. Okay, so let me shortly recall or describe what is a double category. So it's a categorical structure. It has objects. We have two types of morphisms, horizontal and vertical. They're composed within themselves, but not with each other. And we have some two cells which look like squares like this. So X and Y are horizontal morphisms. F and G are vertical morphisms. So alpha is like this cell. I'm thinking of it as like a two morphism. So these compose in both directions. So if I stick another two cell here, I compose along this side, or I can stick a cell here, I compose along here. We have interchange law and things like that. I'm not really concerned to go in details on that. So to me, the very, very nice thing about double categories is this two types of morphisms. I think about it as having an extra degree of freedom with respect to two category theory. I think it's really perhaps underappreciated thing about double category theory. So, so there are lots of examples. In talk from John Baez, we saw like spans, I think, and bimodules already appeared. You can look, I mean, if you look in NLab, you will find, I mean, lots of stuff. So, okay, now, as I said, I will fix V category C, and I will construct a double category, which I've called DC, like this. So I will take the objects from C and the vertical morphisms from C. So here I'm taking technically the underlying category of C, but I mean, I'm thinking of enrichment as like we have a base category with extra structure. So I already have an actual category. So, okay, so the vertical part I want it to be C. Now, this is where I will, in the horizontal part, I will do the stuff I want to do. So a horizontal morphism, so A and B are two objects in C, will be a pair X phi. So X is an object in V equipped with a phi, which is a map in V from X to the, so this is the V object of morphisms. So I want the horizontal morphisms to be these.
When you say the vertical morphisms are those of C, you mean
sorry,
of the underlying?
Yeah.
Okay, great.
Yeah. So the horizontal part is this thing. So I have an object in V equipped with a map to CAB. So how do we compose? Of course, we use the monoidal product in V. So if I have a composable pair, so X comes with a map to CAB and Y comes with a map to CBC. So I tensor and then I use the composition operation in C. So this gives me a map from Y tensor X to CAB, and I take that to be the composite horizontal morphism. And the unit is, of course, the choice of the identity map. So I is an object in V equipped with a map to CAA. So kind of fits into this definition here. If you do the compositions, this turns out to be okay. So, all right, the two cells, this is, I think, the natural choice. So I need to describe to you what is a two cell alpha. So it's a map from X to Y in V such that this diagram commutes. So let's briefly go over it. So I have the structure maps from X to CAB, from Y to CD here. So here I have post-composition with G, pre-composition with F, and this diagram needs to commute. So if this looks kind of weird, let me say this. So if we take V to be category of sets, then C is an ordinary category. So we can think of X actually as representing like a bunch of morphisms from A to B, Y bunch of morphisms from C to D. So alpha cell is a function such that this commutes. So phi X is an actual morphism A to B, and then alpha gives me an element of Y, and when I apply psi, it's an actual morphism C to D, and this square needs to commute. Okay, so so this is my tribute to this symposium. So this double category has companions. So given a morphism in C, well, in enriched category theory, we think of it, I mean, as a map from I to CAB, right? So which makes this pair IF a horizontal map in the structure I just described. So there are these two cells, and we satisfy the conditions in the poster. So if you look at the poster, you will find a definition of what is a companion, and you can verify that this is true. So there you go. Okay, so before, okay, now we can do this. So we had this picture of a lifting problem, and if we interpret it in this double category I just described, so I can stick an identity here at B to kind of make it look like a square. And so this dotted arrow has moved to here, and I can interpret it as a CAN extension. So let me go back here and tell you what these are. So as I said, we have this extra degree of freedom in double category theory with respect to two category theory. It allows, one of the things it allows us to do is to talk about various CAN extensions. So what I will consider here is like, if I have these solid arrows, so two vertical, one horizontal, can look at the universal filler square. So this dotted arrow and the cell completion of this thing, which is universal, meaning any other cell completion factors through a, so there should be a two cell here, right? Just like CAN extensions in two categories. So if you do that, we have this easy to prove proposition. So you take F and G, you do the CAN extension here, you can prove that this is actually this pullback, which makes sense because L, the collection, I mean the V object of lifts, is the stuff between A and C such that when composed with G gives us F, right? So this is easy, very easy to prove. Just follow definition, straightforward translation. So this is just to, so the point is just to see that this gives the correct answer. Okay, so we have enriched, the enriched lifting object L as a CAN extension. So for duality, let me go through this part quickly. So we kind of have to invert the direction of the two cells. So instead of asking for alpha to be a map from X to Y, we ask for it to be a map from Y to X. If you think about it, this makes a lot of sense. again, if you think of things in Y as being kind of morphism C to D, you map them to things in X, which make the square commute. This is kind of the intuition. And we can do this kind of stuff again. So the extension problem becomes this stuff here. And again, we have this pullback, so it works. Okay, so I wanna, so I've got 5 minutes, which is good. So this was like these lifting and extension stuff was more like an excuse to introduce this double category. So another thing we can do, so this is the sort of stuff that triggered me to define this kind of structure. We can understand, or I said,
He is frozen, not just for me. Okay.
He's frozen for me too.
where
Okay, you're back. Sorry, Redi, we lost 10 seconds of what you said.
So it says my internet connection is unstable. So,
but now looks fine.
I think you're about to say something about co-tensoring, but
yeah. So this slide, can you see the depicting tensoring and co-tensoring? Yeah.
Yes.
Yeah, so I'm just recalling the definition of what it means for C to be tensored over the base V. So if I have A in C, X in V, we can kind of multiply. So I have X multiplication or tensor A, which is still an object in C, such that they satisfy this exponential law, which is natural in all variables, etc. So morphisms in C, so this is an isomorphism on sets, but if V is closed, you can do the Yoneda thing and make it an isomorphism in V. So morphisms from X tensor A to B in C correspond to morphisms in V from X to C A B. And these things from X to C A B were my horizontal morphisms in the double category I described. So this is my pictorial way of defining the tensoring. All right, so if I have, so what is this saying? So first of all, I have like if C is tensored, I already have a horizontal morphism A to X tensor A, just by definition, because a morphism from X to this home object corresponds to a morphism from X tensor A to X tensor A. I can choose just the identity. So I always have this top part. And if I choose anything else with X in it, there's a unique way to complete this two cell with the identity X here. And this is precisely, yeah. So if you unpack what I've said here is precisely describing this bijection. So this was kind of interesting from also because this kind of diagram should precisely remind you of the Grothendieck construction or Grothendieck vibrations. So here, oh, okay, so we have Julie as well. Okay, so this is something I haven't done the details yet, but it's kind of there. So there is this double category comes equipped with a functor to the suspension. So this is the one object two category corresponding to the monoidal category V. So you forget everything, and I mean, you take this cell to just this two morphism here, which is the map from X to Y. So this is a forgetful thing. So the thing is that this map, which corresponds to the identity on X tensor A, should be thought of as a Cartesian lift of X. So in the suspension, X is a morphism. So the Cartesian lift of that in D should be precisely this thing which is there by default. And so, I mean, wrapping up these observations, we should have, I mean, I said theorem here because I didn't typeset conjecture, or, I mean, it's just an observation, basically. It says that C's, we should prove such a thing. So C is tensored over V if and only if that double functor is a Grothendieck vibration. So I couldn't, I mean, maybe it's my ignorance, but I don't know of Grothendieck vibration between double categories laid out anywhere. So this is like my excuse to kind of go into that subject. So that these Grothendieck vibrations should be something interesting even without these observations here. But it's kind of a nice thing, a nice way to wrap things together. Of course, there is a dual. I mean, C is cotensored if the dual of D is a Grothendieck vibration or something like that. Okay, so I guess my time is up and my presentation is over. So thank you.
Let's thank the speaker.
Thanks.